Alright, so today we're going to talk about 3.2 on polynomial functions and graph. We've talked about polynomial expression, and now let's view them as machines with inputs and outputs. So they follow the exact same form as a polynomial expression, except this is p of x, so it's a function now. And my inputs are these x's over here. an minus 1, a sub 1, all the way to a sub 0. These are constants in particular, where the first one cannot be 0, otherwise, then we're just going to choose the one next to it. This n is a natural number. That means it's just any exponent number. 1, 2, 3, 4. I don't want fractions in particular, and I don't want negative values. Okay? And of course, I don't want 0. So, let's observe some parent polynomial slash power functions. We've already seen some, but let's revisit some. If I have y equals x, it's just a straight line crossing through the origin with slope of 1. I can have a quadratic, y equals x squared. I can have a cubic, y equals x cubed. I can have a quartic, y equals x to the fourth. And I can have a quintic, y equals x to the fifth. Now, I want you guys to pay very attention. Outside of the first one, all of these follow a similar pattern. If they are even degrees, they're generally going to follow the same form right here. I should draw an arrow here, so let me fix that up. Oh, no, I don't have to draw an arrow. Ooh, I do. Oh. Alright, they all follow the same form. This is second power, this is the fourth power. You can assume what's going to happen or generalize what's going to happen for the sixth, 8, and 10. Now, there are going to be some differences. In particular, the main difference is that it starts to level out at that intersection over here. This one right here, it seems like, hey, it just touches it very quickly, but over here, it kind of levels out all the way until it reaches it, and then it slowly gets out of that x-intercept. Likewise with x cubed to x to the fifth. Has that snake-like behavior in a sense. So, we want to work with polynomial functions which are continuous and smooth. Polynomial functions are continuous and smooth. So it's hard for me to define that for you guys because that's a calculus topic. So I'm just going to informalize that. What this means is that we do not have any jumps or cuts slash corners. So what is a jump? This is a jump right here. How if I'm drawing my function, my pencil eventually has to take a break and jump to the next location right here. That's called not being continuous or discontinuous in particular. So this is not a polynomial function. Likewise, with the idea of cuts and corners, these are cuts, these giant sharp peaks right here. Boom, 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 boom. They are not cuts at all or corners. Or they are cuts and corners, so they are not polynomial functions. Now these regions over here, they are very smooth in how they transition. If they are smooth, then it's a polynomial. But because it has these two cusps, we cannot say this is a polynomial function in particular. So, those are some properties of polynomial functions. Now let's look at some key features, things that we like to look out for. One of them is end behavior. We need to discuss the end behavior of polynomial functions. Now, end behaviors are nice because polynomial functions, we can generalize them for their degree. Degree is the highest exponent. If they're odd degree, we have a generalization. If they're even degree, we have a generalization. Look at above over here. The even degrees have that same kind of behavior like. Same with the odd degree. So what is that behavior? Well, as x approaches infinity, y approaches infinity for an odd degree. So that means as I'm going to left to right, if I'm going to the right side, my y value will blow up upwards. Now, if I read it from x to negative infinity, that means I go left. My y value is negative. It goes down to negative infinity. All right? And I draw these little arrows to kind of give you an idea of how I like to do it. The left side goes up. The right side goes down in particular. That's an informal way to do end behavior, which I like to do. Now, let's talk about even degrees. All right? Like x squared, x to the fourth, x to the sixth power, and etc. If I go to the right side, x approaches infinity, then y also approaches infinity. It goes up. Now, if I go to the left side, if x approaches negative infinity, y approaches positive infinity. So they both go up in this case, the left and the right side. That is very important. All right? This is the general behavior you need to know for polynomial functions. Now, this would be the behavior that you need to memorize or know in general, But the problem is we have transformations. Transformations, the one that it messes with the end behavior, are reflections. In particular, reflections across the x-axis. So what happens if my leading coefficient, or if there's a negative in front of my expression? Then we have a reflection across the x-axis. Here's what it would look like for an odd polynomial. I flipped it. And here's what it looks like for an even polynomial. All right? Now, if they have a negative coefficient or negative leading term or anything like that, they have a new behavior. Everything gets flipped. So as I go from left to right for the odd degree, so if I go from to the right side, I go down instead of up. If I go to the left side, x approaches negative infinity, I go up instead of down. So it reverses. Likewise, with even degrees, if I go all the way to the right, it goes down. If I go all the way to the left, it goes down. You do need to know this flow chart in particular. All right, this is a very powerful flow chart. So now we talk about zeros of polynomial. Zeros are one of the most important concepts in mathematics. Now, they might not be important for some other areas, but in mathematics, that is one of the most important things we talk about. So what are zeros? Well, I'll give you the formal definition real quick. If a polynomial function p of an input c equals 0, we say that x equals c is a zero of p. It is a zero. So what does that mean? That means it has to be all values of x that satisfy p of x equals 0. If I throw that value inside my function, it spits out a 0. If I throw in an input and it spits out 0, it is called a zero. Do you see the naming? All right. So you need to know these synonymous mathematical words. And this is in particular with real numbers, not necessarily complex. We'll go into that later on, 3.5/1.6. So these all mean the same thing if you're in a real plane. Zeros, x-intercepts, roots, and solutions. They all mean the same thing in this case. All right? So we say a polynomial, if p is a polynomial function and c is a real number, if one of these is true, then all of them have to be true. Remember, these are synonymous. So watch. If c is a 0 of p, well, it also has to be an x-intercept. C is an x-intercept of the graph of p. Well, if it's an intercept of the x-intercept of the graph of p, it is also a solution of p of x equals 0. And lastly, x minus c is a factor of my polynomial expression. I can factor out an x minus c in particular. If I wanted to do some factoring, that's one of my components. All right, think of factoring as these, breaking it down to Lego blocks. I have a polynomial function p. If I have an x-intercept, I can do x minus that x-intercept, and that is a small Lego piece for that big giant Lego piece. All right, all four of these are equivalent. If one of them is true, they are all true. You need to know that. Get comfortable with saying that, hey, if I have x-intercept, I also have a 0. If I have a solution, I also have an x-intercept, etc. So let's take this example. This is a polynomial function of degree 3. X times x minus 30 times x plus 2. Some of you guys might argue is degree 1 because the highest exponent you see is 1. However, if I were to fully multiply all this out, I get the highest exponent is 3. This is to the first power, to the first power, to the first power. If I multiply all these 3 together, 1 plus 1 plus 1, by our rules of exponent, we're going to add them. And I get x to the third is my highest exponent. So that is the degree. Now, let's see the solution in particular. All right, let's see the zeros. So p of x equals 0 implies that each one of these must be set equal to 0 because they're all multiplying. If one of them is 0, then it will be equal to 0 because it's multiplication at the end of the day. So I set them all equal to 0. And then I get 0, 3, negative 2 are solutions to p of x equals 0. Likewise, they are zeros of the function p. And because I have these, I can write x minus 0 times x minus 3 times x minus negative 2 as factors of p. Well, if I simplify that, I get x times x minus 3, x plus 2, our original problem. I factored out for you. This is called factored form, by the way. We will talk about that later. All right? So those are the factors. And because they're factors on all this stuff, 0 solutions, we can also say 0, 3, -2 are the x-intercepts of my function or graph. So I can plot those points, and I know it touches those at the x-axis in particular. It touches that -2, 0, and 3. This is a very powerful theorem. Now, again, it's important if I give you one of those statements, you need to be able to infer that the other 3 are true. You need to know that. Now, it's a very powerful mathematical theorem. I do require you to know it, but not to go into too much detail besides definition, the statement really. All right, this is called the intermediate value theorem, and I'm going to give you the weak version. I give you the weak version because a lot of students struggle with the strong version, and eventually we had to find a middle ground. All right, if P is a polynomial function, and P of A, that's the input, if I throw in an A inside it, so I get an output, and P of B, throw in a B, and I get a specific output, have opposite signs. So the output is positive, the output is negative. Or you could say the output is negative, the output is positive. If they alternate in positive and negative, then there exists a C in between A and B, somewhere in the middle, where it's going to be a 0 in particular. It's going to have P of C equals 0. So I do require you to know what this is and kind of know what it means. So let me show you the example of that so you can have a better understanding. It's actually very trivial. And the reason why is because polynomial functions are continuous and smooth. Let's say I have this polynomial function, right? Pretend you didn't see this orange. Okay? I choose a point that's positive. Let's say over here. Let's call this P of A. The x value is A. The y value is positive. P of A. That's the y value, right? So maybe it's like 3, 4 or something, right? And then I have another part of my polynomial function past A. Let's call that B on the x value, right? If I check the output for it, it's negative. It's down here somewhere. Well, because my function has to be continuous, it has to connect to each other. Eventually, no matter how weird I draw this piece right here, I don't know. I might not know what it looks like. I don't know how my function looks like. But however I draw it, it does have to cross this x-axis at the end of the day. There's no way it can avoid this x-axis as long as our function is continuous and smooth, which is a polynomial function. That's what it means. That means there exists a 0. There exists an x-intercept. That's all I'm really saying in this statement, this theorem. Right? That is called the intermediate value theorem, IVT for short. Now, how do you find zeros? How do you find these x-intercepts besides graphing them on your calculator? By the way, if you have a graphing calculator, that's a little skill you can practice. Be able to find the factored form or be able to find the solutions by graphing in particular. So let's take -2x to the 4th minus x cubed plus 3x squared. How do I find the zeros? Well, first, let's factor it. Let's put it in something called factored form. I'm going to factor as much as possible. I factor out x squared. If I factor out x squared, I get this guy right here, this expression. Now, this leading coefficient is bigger than 1, so I'm going to multiply this with the constant to factor it even further. All right? So now I factor by grouping. And then I find the GCF of my grouping factors, and boom, I have this expression right here. Now, this is all multiplication, which is very nice. They're all fully factored, which means I can set them all equal to 0. All right? If I try to set this equal to 0, it's not as helpful because I don't have multiplication happening. But because I do now, set them equal to 0, I have 0, 0, -3/2, and 1 as my solutions. Now, I put 2 zeros here. They are the same values, but you're going to see why I include that, okay? We say x equals 0 has multiplicity too. So this means the x-intercept, or not the x-intercept, oh, it is x-intercept. X-intercept, roots or zeros, they repeat twice. You don't see that graphically, but it does repeat twice. We will see a behavior that happens graphically, though, with multiplicities. So these are my solutions in particular. Now, let's talk about multiplicity. The multiplicity of a 0, of a solution of an x-intercept, is the number of times the 0 repeats. In this case over here, 0 repeats twice because x squared equals 0. This happens twice. This is 0 times 0. So this affects the behavior at the x-axis. So let's look at this problem right here. f of x equals x to the fourth, x minus 2 cubed, x plus 1 squared. If you find the zeros, we see that, hey, my solutions are x equals 0, x equals 2, x equals negative 1. Now, because this is to the fourth power right here, this repeats 4 times. Because it's raised to the third power, this repeats. Oops. Well, I'm going to change that problem then. Boom, boom. Let's just make this squared, just to make our life easy. No, I'm not going to do that. Let's just fix it all. Control Z. And then I want to do, so this has multiplicity, so I miscounted, 3 in particular. All right, this has multiplicity 3. So now I have all these multiplicities right here. This is how much time the root appears or repeats. So now here's a little property that we need to know. If it has an even multiplicity, when it touches the x-axis, it will bounce off the x-axis. If it touches the x-axis, the x-intercepts, with an odd multiplicity, it will cross through the x-axis. The higher the multiplicity, the more snake-like we will behave at the x-intercept. So let's observe this same graph over here. All right? This is 7, 9. It has a degree of 9. All right? If it have a degree of 9, we know the end behaviors. It's odd, so the left side goes down, the right side goes up because my coefficient is 1, which is positive. There is no negative coefficient being multiplied to this guy right here. All right? So now we have to know how to graph it. I'm going to draw my end behavior real quick. I'm going to draw that first. Why did I do it correct over here? Oh, that's strange. All right, I'm going to draw my end behavior. Once I've drawn my end behaviors, this left arrow right here and this right arrow down, up, now I'm going to plot down my x-intercepts. They are -1, 0, and 2. Boom, boom, boom. Now, from the left side right here, I need to know how to behave to the x-intercept. It has to touch it, though. So I'm going to touch it all the way to that x-intercept. Now, am I going to bounce or am I going to cross? Look at the multiplicity of -1. It says the multiplicity is 2. So I have to bounce. So I'm not going to cross that x-intercept. I'm going to bounce instead. And then I have to eventually go back to the next x-intercept right here. So I'm going to turn back and touch that guy. Now, this is x equals 0, multiplicity 4. So it also bounce. Now, this bounce right here has more of a snake-like behavior because the multiplicity is higher. So boom, it levels out more. Now I have to go up, of course, because I'm bouncing. I can't cross it. But I have to eventually go back down to touch my next x-intercept. Boom. Now, x equals 2 has a multiplicity of 3. This should cross the x-axis. So I'm going to cross through it. All right? You should have the graph leading to that other end behavior correctly if you've done so correctly. All right? So this is an example how you can graph. You will be required to know how to graph these. So my tips that I give you is that first, calculate the degree of the polynomial. After you calculate the degree of the polynomial, check the leading term. Is it positive or negative? Once you've checked those, then you can graph the end behaviors. And you should know the end behavior. If it's odd, down, up. Even, up, up. If it's negative on your leading coefficients, it's up, down for odd, and then down, down for even degrees. And then find your x-intercepts, plot your x-intercepts, and then check their multiplicities, and then see how they behave at the multiplicity. Start with your end behavior and go to those x-intercepts. All right? That's how I would proceed it. This is going to wrap up 3.2. I hope you guys have a good day. I will catch you guys next time. Take care. Bye.